Lecture we went over quantum numbers, where they came from, how we get them, how we write them down. This lecture is going to be on how we use them. Why are they there? And how do they help us in gaining an understanding of where the electrons are in an atom? Well, we have some 4 rules that will guide us through orbital notation. But first, before we write orbital notation and before we perform an orbital notation problem, we have to be able to understand where those orbital designations come from. So right up here, I've written down the first quantum energy level. I've written down n equals to 1. L has to equal 0 because the allowed L values are 0 through n minus 1. So n minus 1 here is 0. So the only allowed L value is 0. The only allowed m value is 0. Here I have n equal to 2, and I have my orbital number, my quantum numbers that come out of an n equal to 2. But what does that mean? Well, I listed the main points in the orbital, in the quantum numbers right here. You have a list of 3 quantum numbers. S is always positive or negative 1/2, and that describes the spin state of an electron. So I've left that off because that doesn't matter as much for orbital designation as much as for orbital notation. So here, how do we develop orbital designations? Well, at an n equal to 1, L equal to 0, I have the first principal energy level. So I'm going to write down 1. And I'm going to write down the orbital designation, which here, L equal to 0, is the S designation. Now notice I only have one m value for that L value. That means that there's only one orbital in the S subshell, which means that I'm done. That's the orbital designation. The orbital designation for an n equal to 1, L equal to 0, and m equal to 0 is the 1s orbital. Inside that orbital, I can have 2 possible spin states, positive or negative 1/2. That means that the 1s orbital can hold 2 electrons. Now let's look at an n equal to 2, but now the allowed L values for n equal to 2 are both 0 and 1. Now with an L equal to 1, you only have one allowed orientation. So you yield, if you write out the orbital's designation, the 2s orbital. The 2 comes from the principal energy level. The s comes from what the L value was. The L value here was 0. So I get the s subshell. There's only 2 allowed electrons in the s subshell because, as you can see, the spin state is positive or negative 1/2. Now in an n equal to 2, L equal to 1. Well, our L value changed. So I'm going to write down the principal energy level again. But instead of the S subshell, now my L value is 1. My angular momentum value is 1, which gives me a general different shape of an orbital. Instead of being a sphere, my p orbital is more of a dumbbell shape, which means I have the 2p orbital. Now that goes for all these because the n equals 2, n equal to 2, L equal to 1, L equal to 1. So these are all in the 2p subshell. Now notice that I'm using the word subshell differently than orbital. With the S subshell, there's only one allowed orientation, which means there's only one orbital. An S subshell has only one orbital. But a P subshell has 3 allowable orbitals because it has 3 different orientation numbers. Remember, my M value gives me the orientation about the nucleus. So let's say my orientation for my p orbital, here's what it looks like. I have a 1, or a negative 1. That means that it's in the z-axis, which it's here. So then I'm going to write down my orientation is my z-axis. Now here, I'm going to assign the other m values my other axes. So I get 2pz, 2px, and 2py. Now those are different orbitals. Same subshell, different orbitals. So we're going to designate them different. So the first thing we write out is the designation. Here, my 1s orbital goes first because inherently that's the lowest energy orbital, right? Because it's the first energy level, so it's the lowest energy. So then, after that, I'm going to draw the number of orbitals inside the s subshell. Now, because it's the S subshell, it only has one orbital. Let's move on to the 2s subshell. So once I write out 2s, I write out the number of orbitals. In this case, 1, because I'm still in the s orbital. Now here's the tricky part. Once I move up to the 2p level, I have 3 different orbitals. Now I'm going to have to write out 3 separate lines because these lines designate orbitals. So now look at this. If you see here, I have 1 orbital, 1, 2, 3 orbitals. Now beside the orbital, I'm going to write out my orientations. That's X, Y, and Z. Now you'll see this written out in 2 different ways. You'll see it written out vertically like this, which is my favorite way, or you'll see it written out horizontally like this. Either way, it matches with the increasing energy. So we always write the increasing energy is either bottom to top or left to right, like a mathematical equation. Now you can also see this a third way, right? The third way is to write the orbital and the designation below it. 2px, 2py, and 2pz. Now when we look at these, of course, we have to choose one method. My favorite method is the vertical method because it makes sense to me that you go from lowest energy to highest energy. This also makes sense to me, left to right, but I don't think it's as pretty. So I like the vertical method. The main thing with the vertical method that you have to make sure you keep track of is how many orbitals are in each subshell. Once you write out that, you need to make sure that you keep track of the orbital designations, right? 2p has 3 different orbitals, x, y, and z. Now, what happens when you get above 2? Well, it's really simple. You keep on going. So let's list out the orbitals and then figure out the quantum numbers from the orbitals. So we've introduced the subshells of S and P, but we haven't introduced the other subshells. The other subshells are known as D and F. So what do you think the L values for D and F are? Well, if P is an L value of 1, D is an L value of 2, and F is an L value of 3. D only occurs at the 3rd principal energy level. The F only occurs at the 4th principal energy level. But we'll never go past that. So here's where it comes into handy. And we're going to start off with a big chart. I'm going to draw it out, and this is going to be what's called our orbital filling chart. Right? And we'll explain orbital filling in a minute with our 3 rules. So we have our 1s orbital. Then we're going to go opposite of the way we want. Right? In orbital notation, we work from bottom to top, but here in our orbital filling pattern, we're going to work top to bottom. So we're going to do our 2s, then we're going to list our 2p right next to it. Then we're going to write out 3s, then we're going to write out 3p. Well, at the 3rd principal energy level, you introduce an L value equal to 2, which is the d orbital. So you get the 3d subshell. Now I do 4s, I do 4p, I get 4d, and now at the 4th principal energy level, you introduce an L value equal to 3, which is allowed, so you get the 4f. Now guys, past there we won't go on because once you start filling the F, you get the lanthanide and the actinide series, which, as you can see from the periodic table, it stops. So we really never fill the G orbitals except with excited states. So here we have the 1s, the 2s, 2p. We'll keep on going because it will make more sense in our orbital filling if we just fill out down here. So we're going to fill out 5s, we're going to fill out 5p, 5d, and then we're going to stop right there. Now as we look at this, what we're going to look at is how are we going to fill these orbitals. So let's look at how we write out orbital notation. So the first thing is going to be labeling our orbitals. I'm going to write out 1s. Here's my 2s orbital. Here's my 2p orbital. And then after my 2p, I'm going to have my 3s. Whoopsies. And then I'm going to have my 3p. 1, 2, 3, x, y, and z. And I'm going to stop right there. Because when we talk about a new rule, we're going to talk about something different, and then we'll re-explain the orbital filling patterns. So the first rule of orbital filling is the Aufbau principle. The Aufbau principle is that you always fill from the lowest state to the highest state. You never fill in between and then backfill. You always fill ground to excited. Never anymore. So let's look at the orbital notation for something a little bit more complicated. Let's go to iron, right? So this will be the orbital notation of iron. Now, the thing that you need to know about iron is how many electrons it has. Well, unless I say differently, we're going to assume the ground state neutral atom, which means that it has as many electrons as it does protons. Now, the atomic number of iron is 26. So if iron, it has 26 electrons. If its atomic number is 26, it has 26 protons. If it has 26 protons in its neutral ground state, it will have 26 electrons. Now let's start filling our orbitals. Now the Aufbau principle states fill from the lowest to the top. So if I start out, I cannot start filling at 2p. I can't start filling at 3s. I must start filling at the lowest energy level possible. And as you can see from my chart, that's backwards. My 1s is at the top, so my 1s is at the bottom. So I start filling. Now I fill like that. I've got 2 electrons, right? Because in the 1s orbital, I have 2 allowable spin states, positive and negative 1/2. Now with those 2 allowable spin states, you can see that I have an up arrow and a down arrow. Now remember, the arrowheads can change. You can have a full arrowhead. I draw a half arrowhead. It's up to you as to what you want to draw. I like a half arrowhead because I think it looks prettier. I think it looks better. So you fill with an up arrow and a down arrow, because you always have to have opposing spin states. You can never have the same spin state existing in the same energy level because of what's called the Pauli exclusion principle. The Pauli exclusion principle says that no 2 electrons can have the same set of 4 quantum numbers, which means here I have an n equal to 1, an L equal to 0, and M equal to 0, but these 2 electrons differ by their S quantum number. So they're allowed to be in the same notation. If I drew both of them up as up arrows, they would both have a spin state of positive 1/2, which means they would both have an n equal to 1, L equal to 0, M equal to 0, and S equal to positive 1/2, which Pauli says, nah, not in my house. You have to have different quantum numbers. So as we look at this, we fill 1, then 2. So we've covered the Aufbau principle and the Pauli exclusion principle. The next principle that we're going to cover is Hund's rule. But first, we have to keep filling. So here we have 26 electrons, and we've used 2 of them. We have 24 left. So we fill the next highest energy level according to the Aufbau principle. The Aufbau principle states fill from the lowest to the top. So the next energy level is the 2s. I'm going to fill up, and then I'm going to fill down. Now, how do I figure out which one to fill? Well, that's why we drew this chart. So it's really easy. We start at the top, and I'm going to draw a diagonal arrow down. So here, once I'm done filling the 1s orbital, I'm going to draw it through there. Well, where's the next orbital? Well, I start here, and I say, okay, I'm going to start another parallel diagonal arrow. So as you can see, I start at the top, and I fill from 1s, and then I fill 2s. My next orbital filling will be from 2p to 3s. Great. All right, so now I'm going to look at my next available one, and I'm going to go up to the 2p. Now here's where Hund's rule comes into play, because Hund's rule only governs multiple orbital subshells. And what Hund's rule says is you cannot fully fill an orbital until all equal energy orbitals have been filled with exactly 1 electron in the same spin state that you filled the first one. So here's the deal. It's a consistency rule. So if I start at the 2p, I can't fill 1, then 2. I can't do that. Hund's rule says no. You can't do that. What you have to do is you have to fill each equal energy level a piece before you backfill and fill up the whole subshell. So Hund's rule states very simply that I have to leave 1 as a positive 1/2 spin. Next, I have to move on to the secondary orientation, and I have to fill up that with a positive 1/2 spin. Hund's rule also states that you have to fill all the equal energy orbitals with exactly 1 electron of the same spin state. So I can't fill the Y orientation with a negative 1/2 spin state. That's not allowed. I can't do that. So I have to fill one at a time with positive spin states. Now, as I move across, now that I've filled up all my equal energy orbitals, now I can backfill and refill them in with negative 1/2 spin states. Now I've filled up my 2p orbital. So then now, looking at our diagram, we're going to fill up our 2p orbital, and then we're going to move on to our 3s orbital. So because I only have one orbital, I don't need to worry about Hund's rule. I'm going to fill it with 2 electrons. Now notice that I'm consuming electrons as I go. I've taken up 2 electrons, 4, 6, 8, 10, 12 electrons. So then now, out of 26 electrons that I know that are in the atom, I have now used 2, 4, 6, 8, 10, 12. So I have 14 electrons left to put into orbitals. So then now, if you notice, I'm going to fill from the 2p to the 3s. Now I'm going to draw a new diagonal arrow. And I'm going to draw it from the 3p through the 4s. So then now this is where it gets complicated, and this is where most students struggle. Why am I going to fill the 4s before the 3d? Very simple answer, because it's lower energy. So the Aufbau principle states that you fill lowest to top. And 3d is a higher energy than 4s. Now, why it's higher energy, we're not going to go into that explanation, but I will tell you it is in fact higher, so then we fill up the 4s. Now, there are instances where sometimes because of electron spin and because of field splitting, that the 4s is actually a higher energy than 3d. 3d gets filled before 4s, and then an electron jumps, and that's a more complicated issue. But for general cases in the transition metals, the 4s fills first and then the 3d. So here, we're going to look at this and we're going to say, okay, now I have to fill through Hund's rule. Now, through my orbital filling diagram, I'm going to say my 4s is right here. Because look, I filled from 3p to 4s. Now I only have one allowed orbital, so I can fill that readily. Hund's rule doesn't apply. So now I'm running out of space. I'm going to erase this. So then now I'm going to write my 3d orbital. Because now I have 3d. So now I'm going to fill from 3d to 4p to 5s. But the 3d sublevel has a quantum number of n. The d corresponds to an L value of 2, which means it has an m value, allowable m values of -2, -1, 0, 1, and 2. That's 5 orbitals. 5 different orientations. So I'm going to write out 1, 2, 3, 4, 5. So then now, as I look at this, I'm going to say, okay, how many electrons have I used? I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. How many do I have left? Well, I have 26 total in the neutral iron atom, so I have 6 total electrons left. Here's where Hund's rule comes into play. Because Hund's rule states I have to singly fill each orbital with the same spin state before I backfill. So I can't just go 1, 2, 3, 4, 5, 6, and only have 3 filled orbitals and 2 unfilled orbitals. I have to fill one at a time and then backfill. So I'm going to fill them all with positive 1/2 spin state. And that takes up 5 electrons. So now I've used up 25 electrons, and now I have 1 electron left. Well, that 1 electron goes back, and it backtracks, and it backfills into that orbital. So now I've used up all 26 electrons. Now you might be asking me a couple of questions. Number 1, where are my d orientations labeled? Because I have x, y, and z here. The d orbitals get into some funky stuff, and so we have d orbital designations of x, y, y, z, and x, z, and then we have d orbital designations of x squared minus y squared and z squared. So the orbital designations are funky because the d orbitals split, and they're not just orientations in 3D space, but they actually change the general shape of the orbital. So wherein as p orbitals are all dumbbell shaped and they have different orientations in space, one d orbital has a toroid in it, another couple have kind of lobes like in your brain, but they have 4 of them, about an x and y and z axis. So we don't deal with it. We just leave orientations off of the d orbitals, and we just put it on the stuff we can handle, which are the p orbitals. So now you might be asking, okay, what's such a big deal about filling orbitals the way we do? Well, if we didn't fill like Hund's rule said, we would fill the orbitals like this, which would mean that we had 3 filled d orbitals and 2 vacant d orbitals, which would not explain the bonding patterns of iron. We would say, oh, all our orbitals are filled and we have none left over for sharing. We don't see that bonding pattern. What we see is more of an orbital sharing. So what we have to do is we have to follow Hund's rule and we have to put the electrons up here. This will make a lot more sense in chapter 6 when we talk about chemical bonding. Because chemical bonding will be occurring between 2 half-filled orbitals, and they'll combine and they'll share 1 electron in between the 2 orbitals, and those orbitals generally have to match up. So it's very important to understand that Hund's rule states that our orbitals fill a certain way. It's also important to understand that Aufbau states that you fill from the lowest energy level to the highest energy level. Now, how do we decide which one's higher than another? Through our orbital filling diagram. Our orbital filling diagram is a very easy way. If you write it on a test, boom, done. You know how to fill orbitals and you'll never have a question on orbital notation. So let's do another problem and let's see this in effect and let's move through it quickly. So let's use the example of carbon. Carbon has 6 protons. So carbon has 6 electrons. Now, unless I say otherwise, we're always going to assume the ground state neutral atom. So if I say carbon, it has 6 protons, well then it's got to have 6 electrons because it has a ground state. So then now here I'm going to start off with my orbital designation. I'm going to start off with 1s, then move to 2s, then move to 2p. Right? So right here, start off with 1s, I'm going to draw my orbital. Then I move to 2s, I'm going to draw my orbital. Then I move to 2p, and I'm going to draw all 3 of my orbitals, and then fill in my designations. Now, how do we know when we stop? Why wouldn't we just keep going and write 3s, 3p, 4s, 3d for every element? That would get exhausting. We don't do that. How do we know when we stop? Well, when we stop is when we're at the highest principal energy level. How do we know we're at the highest principal energy level for that atom? Well, we know by the period number. Carbon exists in the 2nd period. So then the highest principal energy level that carbon can obtain is the 2nd principal energy level. If you're in the 4th period, the highest you can obtain is the 4th principal energy level. So that would make sense because then we would fill all the way through 3D, taking care of all the transition metals and the 4p levels. So if you look up at the periodic table and we were to choose, let's say, zinc. Zinc appears in the 4th period. So we would write out every orbital that occurs up till the 4th period, which in zinc's case would be through 4p. Right? We wouldn't write out 4d because 4d occurs 1 period behind in the 5th period. Does that make sense? Because it lags behind the s orbital. Right? So now, going back to carbon. Carbon has 6 electrons. It occurs in the 2nd period, so we only write out to the 2nd energy level. Now we're going to fill the 1s orbital. That 1s orbital gets filled because there's no other orbital, so Hund's rule doesn't apply. Then we fill the 2s orbital. Now we run into Hund's rule, because Hund's rule states that orbitals of equal energy have to be half filled with the same spin state before they're fully filled. So now I'm going to fill up the 2p orbital half filled with all spin states. But wait a second, I've used 2, 4. How many electrons do I need? 5, 6. I don't need that electron. So now with carbon, I have 2 half-filled p orbitals and 1 unfilled p orbital. And this is extremely important. There is a reason why I chose carbon, because carbon forms the backbone of all carbon-based life forms. It is the most chemically abundant, you can say, of any element. It's the most useful. Everything around us contains carbon. And carbon is so useful because of this orbital pattern. Now, if we didn't follow Hund's rule and we put this electron with this electron, carbon wouldn't have the same chemical reactivity. But because it has 1 unfilled and 2 half-filled, we can hybridize carbon's orbitals. That will come in Chapter 6. But here's the deal. We have to follow the rules. The reasons why I keep stepping to Chapter 6 is because a lot of students forget about the rules and go, well, what's the purpose on the Aufbau principle? What's the purpose on Hund's rule? Well, it comes in hugely into play when we talk about chemical bonding. Chemical bonding must have certain orbitals half-filled, certain orbitals empty, and that's why Hund's rule is so important. And this concludes our orbital notation.